welcome everybody from myself as well. Thanks for being virtually with us. It's not quite the same as being able to smell and hear the city, but it will have to do. However, this remoteness brought us a special treat. Alain Comtet usually will not travel very far and wouldn't probably come to New York City, but he agreed to participate. Moreover, he had never given a Zoom talk before, but he obliged by doing it just for us. So Alain will talk to us about, will give us a review about his fundamental work on Landau levels on the hyperbolic plane and trace formulas. Alain.
Okay, thank you, Alexios. So the title of my talk is Landau levels on the hyperbolic plane and trace formulas. And in fact, in this talk, we will review certain links between classical mechanics and quantum mechanics. Both theories involve very different concepts. Classical mechanics involves geometric entities such as orbits, whereas quantum mechanics involves spectral entities, spectrum, wave functions. The fact that there is a link between these two theories, of course, is very old. It goes back to the foundations of quantum mechanics, where the EBK quantization rules were introduced. These quantization rules allowed to compute approximatively the spectrum of certain systems. But these rules are very special. They are based on action angle variables, and therefore they require the existence of invariant tori. Therefore, they are limited essentially to integrable systems. Now, since most of you are interested in chaotic systems, for chaotic systems, these rules do not apply. So one needs a substitute for EBK, and these substitutes are the famous trace formulas. These trace formulas were introduced in the physics literature by Gutzwiller in the 80s. And of course, the starting point is much older. The starting point is this Van Vleck formula, which gives the time-dependent propagator as a sum of a path which joined x and x prime in time t. So this propagator is given as a sum of all paths with their action, which appears here, and the second derivative of the determinant of the action, which gives the prefactor. There is an index nu, which is called the Maslov index. Okay, this is very good, but this is not really what we need for chaotic systems. In fact, Gutzwiller, in fact, had made the important observation that one should look for closed orbit, not in ordinary space, as it is the case here, but in phase space. Here, a generic orbit will not be closed. I mean, the momentum, the final momentum will be different from the initial momentum. So by looking to closed orbit in phase space, one can derive a formula, say for the partition function or density of states. This is essentially the same. And this formula is the following one. Density of states is a sum of two terms. A first term, d0 of E, which is a smooth term, which describes the smooth density of state of the system, and a sum of terms which describe the oscillation around this smooth density of states. And these oscillations are related to classical orbits. You have an infinite sum over all periodic orbits, primitive pre-periodic orbits, PPO, of action SP. N is an index, which means that this orbit can be traveled many times. So it's a repetition of the same orbit. MP is the stability matrix of this orbit. And TP is the period of a primitive orbit. So this works quite well for a certain number of chaotic systems. This has been exploited in various papers of Gutzwiller, in fact, although it suffers from some difficulties. One of the problems is that this sum is not really convergent. And the other problem is that this is an approximate formula. It is not exact. It is derived in a semi-classical way in the limit h bar going to 0.
Can I ask a question, please?
Yes.
Okay. I think I must be misunderstanding something. If I have a generic chaotic system in large enough dimension, how does one find periodic orbits? Are there many periodic orbits or just few?
Oh, yes. I mean, to find them, you need, there is no way to find, I mean, you have to do it numerically, in fact.
But even as a matter of principle, why should they exist? For an orbit to come back to itself.
Okay. Why should they exist? It's not completely obvious, in fact. Yes, it's not completely obvious. In fact, you can find, in fact, what has been done so far exhibiting certain systems for which one can find a coding of these periodic orbits, in fact. They can be coded and by an alphabet, and but there are very few systems for which one can really use this program. This is a very difficult problem, in fact. So this comes to my to the main point, which is the fact that there is a formula in the mathematics literature, which is called the Selberg Formula, for which this formula is exact. But it holds for a very, it holds only for a very specific class of systems. It applies to free motion of particles moving on compact manifolds of constant negative curvature. So coming back to this Selberg formula, you see that it has exactly the same structure as the Gutzwiller formula, except now that instead of having the action of a closed orbit of energy E, we now have the length of a periodic orbit on this manifold of constant negative curvature. And one can prove that this formula is exact. It gives the exact density of state and exact partition function. So one of my goals will be to explain the idea which are behind this Selberg formula.
And, a quick question. I'm sorry
yes.
to interrupt. So it's a partition function of what exactly?
Okay, it is a partition function of the free Laplace operator on this manifold. So exponential minus th, where h is minus the Laplacian. You see? So I will explain that. So
is there a notion of temperature here, or what?
Oh no. I mean partition. So partition function. No. There's no notion of temperature. In fact, partition function is just the Laplace transform of the density of states. So let me start. In fact, to maybe this will be helpful to show what is the essence of this trace formula. Let me start by a very trivial exercise. Probably it will be too trivial, but it shows the idea. So this model that I would like to discuss briefly is a 2D rectangle with periodic boundary conditions. So we have, in fact, it is the torus. So we have a free particle moving on the torus. So this is just a very simple exercise. So we have to solve minus Laplacian psi equal E psi with periodic boundary conditions in X and Y. So the eigenvalues are written here. They depend on two quantum numbers, N and M, and you can form the partition function, which is here. And now there is a trick, which is well known. This trick is to replace this sum using the Poisson formula. So using the Poisson formula, you can replace this double sum over N and M as a double sum over P and Q, which is this one. And now these indices P and Q have a very different meaning. As physicists, we should think of them as representing winding numbers, which represent the number of times that a certain trajectory, a periodic trajectory, has wound around the torus. So I claim that the physical interpretation of the right-hand side is that this is really a sum of the paths on the covering space. And the idea is that any closed path on the rectangle can be lifted to a path on the covering space. And this path, in fact, will be closed provided the endpoints on the covering space are identified by a certain discrete group action. So let me show on the figure what I mean by that. So let us consider a particle which starts from here at point x0 and y0, which is sent with a certain velocity. It reaches this side, it is reflected, it reappears on the other side, etc. So if you unfold this trajectory on the plane, it looks like that, in fact. So this is a segment now with ends x0, y0, and x0 plus 2a, y0 plus b. And this will be closed provided these two ends are related by a discrete translation here, a translation 2ab. So you can code all the trajectories on the rectangle in this way. And you can, in fact, you can now look at the contribution of those trajectories in the path integral. So the path integral is the path integral of a free particle. So the motion is free, but when you impose the fact that the periodicity conditions, this fixes the velocity Vx and Vy. And when you put all this in the partition function, which turns out to be exact because this is a free problem, saddle point approximation will be exact, then you get back your Poisson formula. So the partition function is indeed a sum over all periodic geodesics. And here, these periodic geodesics are indexed by P and Q, which are related to a subgroup of the translation group, which acts on the Euclidean plane. So now what we have to do, in fact, is to extend this construction, which holds for the Euclidean case, to the non-Euclidean case. So we will have to replace free motion on R square by free motion on the hyperbolic plane. The isometric group of R square is the Euclidean group. It will be replaced by the isometric group of the hyperbolic plane. And there is a discrete group action, which is essential, as we saw, which is the translation group. Here, it will be replaced by a certain subgroup of SL2R. And the closed surface, which is the flat torus, will be replaced by a certain Riemann surface. So these are the different steps that I would like to discuss, to review. And then we will see how magnetic fields appear in this game. Okay. So first, I have to review a certain basic number of things about the hyperbolic space. So hyperbolic space has different realizations. It can be realized as hyperbolic plane or unit disk. Here we will consider the hyperbolic plane, which is the upper half plane of the complex variable z equal x plus iy. And so this is this upper half plane. We will endow this upper half plane with a metric, which is the flat metric times a conformal factor 1 over y squared. So this metric is conformally flat, and I call phi the conformal factor. Using this conformal factor, you can compute very simply the curvature, which turns out to be equal to -1. So this is a space of constant negative curvature. Now, if you want to study the motion of a free particle on this space, you have to write down the Lagrangian. which is a free Lagrangian, a purely kinetic term. You write down the equation of motion and you solve them. And here is the general solution of the equation of motion. So let us try to represent what is the meaning of this of these solutions. So here I start in the upper rough plane at the point A at time t equals 0, and I send a particle with a certain velocity along x. The particle will follow this arc of circle here, and it will take an infinite time to reach the boundary, which is here the x-axis. You can see here that only for t going to plus infinity, x of t goes to r plus x0. So this is a certain geodesic line. You have different geodesic line. For instance, if you start with a positive velocity along y, you will get this geodesic line, y equal y0 exponential t. But in fact, both are straight lines in the sense of hyperbolic geometry. You should not consider them as different. In order to clarify this point, let me show that there is a very simple mapping between these two trajectories. For that, we have to define the isometry group. So first, we have to define the notion of a distance on this plane. Distance is the distance along the geodesic, which passes by the 2 points, Z1 and Z2. So this distance, you can compute it very simply, and you can express it as a function of the initial and final point by this formula. It turns out that this distance, which is not the Euclidean distance, is invariant under a certain subgroup, a certain group of transformation, which is the special linear group SL2R, which is the group of matrices with real entries, determinant 1. And this group acts on the hyperbolic plane in this way, via Möbius transformation. If you start from Z, which is X plus IY, you apply this matrix G on Z in this way. So you form AZ plus B over CZ plus D. You get another point, which is the image by the group G. And you can check that the distance between Z1 and Z2 is the same as the distance between GZ1 and GZ2. So we have a group of isometries, which is identified, which is SL2. So this now helps to understand more clearly the nature of these geodesics. For instance, this geodesic line, you can map it by a suitable G on this one. You see, they are the same in some sense. You can move one geodesic to the other. As in the Euclidean space, you move a line into another line by an action of the Euclidean group. Not only that, but you can consider the motion on a given geodesic line. If you fix the initial condition Z of 0, you can get Z of t by acting over on Z of 0 by a certain SL2 matrix, which here you have a certain subgroup of SL2, which is an hyperbolic subgroup. So you can view these lines, in fact, as flow lines of a certain subgroup of SL2. Okay, this may seem a bit strange. So I would like to show a very simple geometric interpretation of these geodesics, and which will make the things more clear, probably. So the geometrical interpretation is the following one. In fact, this hyperbolic plane, which is two-dimensional, we can realize it as a two-dimensional surface embedded in a higher dimensional space. It is not Euclidean space, it is three-dimensional Minkowski space. So you start from three-dimensional Minkowski space with this metric, and you consider you consider in this space this hyperboloid minus y0 square plus y1 square plus y2 square equal -1, which is drawn here. So this is a certain two-dimensional surface inside this three-dimensional space. As any two-dimensional surface, it can be parametrized. So it's like a sphere in R3, except for the sign, in fact. So you can parameterize, not in terms of theta and phi, but in terms of x and y. So with this constraint is satisfied. And now the nice thing is that if you look at the induced metric on this hyperboloid, that is the Minkowski metric, which is restricted to the hyperboloid, you get back our metric from which we started. So this Poincaré metric is in fact the restriction to the hyperboloid of, you see? Okay, so in fact, this also helps to understand certain properties of the geodesics. So the geodesics in three-dimensional space can be constructed very simply by cutting the hyperboloid by a plane. So this is the result. You have a certain geodesic here, which is obtained by cutting by the plane y1 plus x0, y2. So if you look on the hyperbolic, on the two-dimensional plane, it will correspond to this geodesic line. Okay. Now, concerning the isometries, this Möbius group, in fact, it comes very simply from the Lorentz group. Indeed, the pseudosphere that we considered, in fact, is by construction invariant under Lorentz transformation.
Alain, there is a request that if you can zoom the slides a little bit more, some people.
Okay.
Yeah, okay, perfect. Yeah.
Okay. Indeed, if you apply Lorentz transformation on the hyperboloid, you will stay on the hyperboloid. So this will leave the hyperboloid invariant. So any Lorentz transformation can be constructed either from a rotation or from the product of rotation and certain boosts. Here you have one rotation only in 3 dimensions, rotation in the y1, y2 plane, and 2 boosts, and their image in hyperbolic plane is just are these elements G1, G2, and G3. So the image of rotation is still rotation. The image of a boost is this diagonal matrix. And the image of the second boost is this one. Okay. So we understand some of the subgroups in a very simple way. These are just the subgroups of the Lorentz group. Okay, but this is, this choice that we have made is in fact to a certain extent arbitrary. You could imagine to start from different subgroups. For instance, inside the hyperbolic group, there is a nice subgroup, which is very natural, which is the subgroup of these matrices. They just correspond to translation along X. When you change X in X plus lambda, this is the action you need. If you look from the Lorentz group part, this is still a Lorentz transformation, but it looks very unusual. It's not familiar to us. It would be familiar, in fact, to Wigner, because Wigner studied the little group in some of his papers. In fact, you can show that this group leaves the light cone invariant. And the light cone, in fact, can be thought as the boundary of this hyperboloid. And correspondingly, this transformation, they leave the boundary of H invariant. Okay. So now let me try to recapitulate the various subgroups that we will need. And in fact, there is an intrinsic characterization of these subgroups in terms of their trace. So if you take a 2 by 2 SL2 matrix, it belongs to one of these three classes. It is either hyperbolic, elliptic, or parabolic. So hyperbolic transformations, in fact, are defined by trace of G larger than 2.
Sorry.
Trace of G larger than 2. And you can show that they are conjugate to Lorentz boost.
Alain, there is a question here.
Yes.
Yes, so I was wondering if it was easy to see that the Mobius transformation's action on Z is linear.
Ah, okay, this one. Yes, here you see, you have A equal 1, B equal lambda, C equal 0, and D equal 1. So you replace here AZ plus B over CZ plus D. So it will give Z plus lambda over 1. So this is just a transformation Z prime equals Z plus lambda. You see?
Right.
And Z prime, so it means X prime equal X plus lambda, since lambda is real, and Y prime equal Y. So this is very simple, you see, as in terms of Mobius transformation. This is a translation along the x-axis. But if you view it from the pseudosphere, it's a very fancy, very strange transformation. This is interesting, in fact. Okay, so it's interesting to have both pictures at the same time.
But
okay.
Is G4 the only one that's linear? So does
that
mean...
G4, in fact, yes. Yes, in fact, you can, if you set C equals 0, you will have Z prime equal AZ plus B over D. So this is linear. And so this will be the combination of a dilatation, and translation, in fact. But okay. But basically, yes, this is the linear transformation of those ones. Yes. Yes.
So you need C to be 0 in order for it to be a linear action.
Yes,
okay.
Yes, you need C equals 0. Yes,
okay.
Exactly. Exactly.
Thank you.
Exactly. Okay, so let me come back to this classification. So we have this hyperbolic transformation, which correspond to diagonal elements of SL2 of this form. Their trace is larger than 2, because their trace is CH phi over 2. And if you look at this transform, at the flow lines of this transformation, flow lines, and by flow line, I mean you start from one point, Z of 0, and you act with a certain matrix G of T. T is phi. Think of phi as being T, and you get another point. And so the flow lines are these lines, either the vertical one or any line which passes by the origin. So these are all the flow lines of hyperbolic transformation. But when you should understand that you can play with conjugation. I mean, if you conjugate this matrix by G and G minus 1, you can transform this geodesics, for instance, to this one. In the same way, this line will be transformed to this line here, which is not a circle, but it looks like a circle. Okay, so these are the flow lines of hyperbolic transformations. In a similar way, elliptic transformations correspond to matrices whose trace is less than 2. They are realized as rotations, and their flow lines correspond to these circles. And parabolic transformation, which correspond to the little group of light vectors, they correspond to this transformation, and they are translation, as we saw. The flow lines are these lines. You see, you stay at the y is constant. You just change x and x plus lambda. So this is really the flow line. But if you perform a conjugation, you can go from here to here. So the flow line is also this one, which is an arrow cycle. This is a circle which touches infinity at this point. So now the link with magnetic field is the following. So the question, a natural question one can ask when you see all these figures is the following one. Is there a dynamical system with these flow lines? Up to now, we have seen that the geodesic flow has the flow lines were either this geodesic, the vertical one, or the circle. But here we have other lines in the hyperbolic plane. And it turns out these lines are flow lines of, our trajectories of magnetic geodesics on the hyperbolic plane. So let me show you. You will see that this is very simple. Okay, so...
Sorry, may I ask you a quick question? So
yes.
Could I think about this as simply cyclotron orbits? If you
okay, we will see. Certain of these lines can be thought as cyclotron orbits, but only those which are closed, in fact. So in fact, we will see that certain of these lines go to infinity. In fact, when the magnetic field is not strong enough, the effect of the curvature is stronger than the effect of the magnetic field, and the particle will escape to infinity.
But isn't it simply the radius of cyclotron orbit versus the curvature radius?
No. It's a different effect, in fact. No. The particle really goes to infinity, in fact.
But if I crank up the field and make it so strong, it will go in circles. How does the particle know?
Yes.
It wouldn't do that. Right?
Sorry?
If I make the magnetic field so incredibly strong that the cyclotron radius is basically very small, so then it wouldn't even know it's on a hyperboloid, right? So it will just
yes, okay. I will come to that. Yes, if the magnetic field, in fact, is stronger than the energy, than square root of the energy, the motion will be on, as you say, on these cyclotron orbits. But this will hold only if this condition is satisfied. Okay, let me briefly show you how this works, if you want. Okay. So first, let me remind you what is a constant magnetic field, because this is not completely obvious. In fact, by constant, we mean, since the magnetic field is a two-form, that this two-form should be proportional to the volume form. So the magnetic field should be, in fact, B over Y squared. So the curl of A is B over Y squared. It's not constant, but B over Y squared, which is B square root of G, square root of the determinant. Okay, and you can solve for the A field. Okay, this is the gauge dependent. Okay, you can choose this gauge minus B over Y and 0, and you get this Lagrangian. Okay, so this is the Lagrangian, like the Landau Lagrangian, except that you have changed the kinetic term and the coupling to the field. But it is essentially the same idea. You have a charged particle which is moving in a plane which has a constant negative curvature. And you can check by using Noether theorem that you still have invariance under SL2R. This is not completely obvious, but it can be shown. You have three constants of motion, which corresponds to the three subgroups which are left invariant. So you can compute these three constants of motion and show that they are indeed constant. And here I have written them in terms of x and px, y and py. Okay. And now the Hamiltonian is written here. In fact, there is a mistake here. There is a y square which is missing. Okay, but the Hamiltonian is quadratic in these LIs. And what is nice is that one can get exactly the classical trajectories without making any calculation. In fact, it suffices to eliminate px and py from these equations, and you plug this into the last equation, and you get the equation of motion. And naively, you would say, okay, you will get, this is the equation of a circle. Okay, it's the equation of a circle, but only in Euclidean space. it's not an H circle in the sense of hyperbolic geometry. In fact, an H circle in the sense of hyperbolic geometry is the set of points which are equidistant from a given point, x0 and y0, and its equation is this one. Okay, it looks very similar, but it's not exactly the same. So by comparing these two equations, you see that this is indeed the equation of an H circle, provided x0 equal L1 over L2, which is always possible to realize, because x0 is, the sign of x0 is arbitrary. But if you try to match these two things, you see that this is possible only if B is larger than 2 square root of E. Only in this condition is y0 is positive. That is, the circle is a real circle in the upper half plane. So in order to have a cyclotron orbit, you have to fulfill this condition, in fact. Okay. What about the other orbits? Because this is not always realized. So again, there is a very nice interpretation, which is purely geometric. In fact, you should not do any calculation. And the idea is to go back to this pseudosphere coordinates. If you write the equation of motion of the trajectories in terms of the coordinates on the pseudosphere, you get this equation, which is linear in terms of the pseudosphere coordinates. So you have this constraint. In fact, when B equals 0, this constraint is in fact conservation of angular momentum. Here it's slightly different. So you have this constraint plus the fact that you are on the pseudosphere. So this means that the particle is moving in the plane. This is the equation of the plane. And at the same time, it's moving on the pseudosphere. So the trajectories are at the intersection between the plane and the pseudosphere. So you can guess what will be their shape. Okay, but you can compute, of course, everything analytically. In fact, here is the summary. The different trajectories are classified according to the sign of J square, which is more or less the square of the angular momentum, except that here you have a minus sign, which comes from the fact that you have a non-compact group, or say that you have the Lorentz group, which is behind. So maybe I should skip this. Okay, but okay. The result is that one can find all the classical trajectories. They are either of this type, which means that the particle will ultimately go to infinity. It will leave, the magnetic field is not strong enough, or of this type, or elliptic, corresponding to the elliptic subgroup, which correspond to closed cyclotron orbits. Okay, so here we have a complete classification of the orbits. Okay, so now let me come back to the case where B is non-zero. And let me summarize. If you remember, at the beginning, we had the problem of the torus, and we showed that the trajectories, on the covering space are straight lines, but in order to go to the torus, we had to identify the points, some of the points of the trajectories under the translation group. Here we have to do the same, except now the trajectories are not straight lines. There are these geodesics on H. And what we have to do is identify points on these geodesics under the action, not of the translation group, but of a certain subgroup of SL2. Okay, so this is done in the following way. So you start from a geodesic, which is globally invariant under G. And so, which means the following. If you have some point Z0, if you act on this point by a matrix G, you will stay on the same geodesic. But what we want to do is consider that these 2 points are the same. I mean, like in the case of the torus, in fact. We want to, in fact, mathematically, we want to, this arc of circle will descend to a closed loop on gamma over H after this identification. And this is possible provided the matrices G are of a certain type. In fact, if you compute the length of this loop by using hyperbolic geometry, you find that the CH of the length is related to the trace of G. So the final formula is that twice the cosine hyperbolic of the length of this trajectory is the trace of the matrix. So since cosine hyperbolic is larger than 1, this requires that the trace of the matrix is larger than 2. So the matrices that come into this game are necessarily hyperbolic matrices. So the result of this discussion is that to any hyperbolic matrix, you can associate a periodic orbit. And its length, it can be read from the expression of the matrix. If you diagonalize this matrix, which is, in this form, which is possible since the matrix is hyperbolic, lambda will be the length of this orbit. But the correspondence is not 1-to-1. M-1 GM gives the same orbit, same trace. So the correspondence is between closed geodesics and conjugacy classes of hyperbolic elements of gamma. And in this operation, the torus will be replaced by a certain Riemann surface with a certain fundamental domain. So here I have represented a figure that all of you have seen in the literature. This is the fundamental domain of SL2Z. So this is this domain which replaces the torus. And if you act on this fundamental domain by one of these matrices or the product or their inverse, you will get a similar domain. And all these domains will tessellate the hyperbolic plane. Okay, so this is the picture. So you see that in some sense it's very close to the flat torus, except that the group which is acting is not the translation group, but a subgroup of SL2R. Okay. Okay, this closes the classical mechanics part. And now we should look at the quantum mechanics on this space. So first, consider the case where when magnetic field vanishes. So quantum mechanics, can be, the quantum Hamiltonian is obtained by classical quantization of this classical Hamiltonian, and you get this differential operator, in fact. So it's almost the Laplacian, except that you have this y square in front, and you can show that this is, in fact, the Laplace-Beltrami operator on this hyperbolic plane, which is an intrinsic object, which doesn't depend on the system of coordinates.
Sorry, may I ask a quick question?
Yes.
So is ordering important here? So...
Yes, in fact, yeah, there are ordering problems. I skipped them, but when you write, so when you write, so this is clearly the classical Hamiltonian, and there are no ordering problems. But when you go from here to here, you have a priori the ordering is not fixed. But this is discussed in my paper. In fact, you can show that it will at most bring some constant factor, but it will not change. It will be this plus eventually a constant term.
Thank you.
But this is the only way, this is the only operator which is really reasonable, in fact. And in fact, this operator also has the good taste of being self-adjoint, which is required for a good Hamiltonian. It is self-adjoint with respect to this inner product. So you have a good spectral problem, minus Laplacian psi equal E psi. And now the Laplacian is a bit complicated, but you can nevertheless solve this problem. Okay, so you can either solve it by separation of variables, by finding the special functions, or by a group theoretical approach. So maybe let me skip the group theoretical approach and let me show how the wave function look like. Okay, so what I call C is essentially the Hamiltonian. And the eigenvalues, in fact, can be written in the form J plus 1. The reason is that you have SL2, which is acting, but J is not an integer. J is 1/2 plus IK. But you can label the wave, you can label the states in this way, but J is complex. Okay, this is just a nice parametrization. And so you can diagonalize the Hamiltonian and, for instance, find the states which have a given energy and a given momentum. Let us call P the momentum along X. So states of given energy and given momentum are written here. Okay, this is a bit unusual because you have this Bessel function, but here you recognize something that everyone knows, which is a plane wave along X. Okay, so this is why you have this.
It's a Gaussian.
Okay, so this is a plane wave along X, but in the Y direction, it's a bit strange. Okay, it's like that. And this solves the spectral problem on the full hyperbolic plane. But of course, the full hyperbolic plane is not very interesting. What you would like to have is something like a torus. So what we want to do is solve the quantum mechanics, not on the full plane, but on a Riemann surface. So let me show on a very concrete example.
This is zero magnetic field case.
Yeah, for the moment, there is zero magnetic field. Then we will come to the case with magnetic field. But first, let us see how this works. Okay, so the spectral problem now, if you take a finite, a surface compact or non-compact Riemann surface, the spectral problem will be to diagonalize the Hamiltonian and impose certain boundary conditions. Now, these boundary conditions are not the same as in the case of the torus, but in spirit, they are quite similar. Psi of Z has to be equal to psi of GZ. So this is a sort of periodicity condition, but periodicity with respect to this subgroup of SL2. So for example, let us consider a very simple case. I claim that this wave function is a wave function, a realistic wave function on this domain. Why? In fact, this domain corresponds to the quotient of H by discrete translation. In fact, this strip, is the fundamental domain which is quite obvious in this case, because if you take this strip, you can transport it, you get the same strip, etc. And now the idea is that you should glue this line with this line. And in this gluing process, instead of having a cylinder, you will have a cylinder, but this is not a real cylinder like the one you are accustomed with. It looks like this one. The reason is that the distance here is not as the same as this distance here. When you go upwards, the distance shrinks. So this is a cylinder with a sort of spike at infinity. So it looks like a horn, an infinite horn in two directions. So you have a horn with a very thin spike here, and it goes at infinity also in the other direction. It's amazing because there are music instruments which look like that. In fact, I have a friend who plays a cor des Alpes in the mountains, and it's exactly the same shape, except that it is not infinite, of course, but it's very long like that. And it gives a very strange, a very unusual sound. In fact, the music played by Corps des Alpes is very interesting, in fact. Maybe the reason behind is that you have this K function, I don't know. Okay, but now let me explain, starting from this example, how one can think of more physical problems. In fact, instead of, to this wave function, you can add, in fact, two terms which are also eigenstates of the same energy. And they are zero modes in the x direction. And so this is, I claim that this is a very respectable wave function, but it has now a very interesting interpretation. The reason is that each term here, this one and this one, can be thought as a plane wave. Why? The reason is that this term can be written as square root of y times exponential I k log y. But log y is the distance in the y direction in this metric. So it's really a plane wave, and it is an outgoing wave. If you look at the wave front, omega t equal k log y, when t increases, the wave front goes upwards. So this is an outgoing wave. In a similar way, this is an incoming wave. So now you can think of a realistic scattering problem, not on the cylinder, because on the cylinder you have no scattering in the same ways that on a cylinder with such an instrument you cannot play music. You have to put your mouse somewhere. You need an instrument which is semi-infinite. Huh? So here you have to close the cylinder on one end, and one very nice idea which is due to mathematicians, but which was exploited a lot by Gutzwiller in '77, is to close the cylinder in the following form. So you consider this fundamental domain, which is like a torus. This side is identified with this side by a certain matrix A. This side is identified to this one with a matrix B. So this is really a torus, except that now you have these points at infinity here, in the y direction. This was clear in the cylinder picture. So this torus, which was called the leaky torus by Gutzwiller, looks like this, in fact, if you would like to see it in 3D, which is not possible, but topologically it's like that. You have a sort of spike which goes to infinity, and here you have a real torus, and you can set a scattering problem on this torus. You can send a wave. The wave will be scattered by the torus on the torus because the system is chaotic. It will be very complicated, but you are sure that you will have an outgoing wave with a certain phase shift. And what is very remarkable is that in this case, you can compute exactly the phase shift. In fact, this calculation was initially done in the maths literature. This is due to a French mathematician, Godement, and then it was extended by Fadeev and Pavlov, and also by Latz and Phillips in their book. Okay, I don't want to go through the calculation, but just mention that this phase shift is in fact related to the phase of the zeta function, Riemann zeta function, which is very remarkable. And I invite you to look at Gutzwiller paper because he drew this phase, and he realized that this phase is indeed a very irregular function of the energy, which is a signature of the chaotic properties of the classical mechanic, of the classical underlying classical problem. So this is a very chaotic problem, a very non-trivial problem from the classical mechanics point of view, but nevertheless, you can compute the phase shift exactly. And in one of my papers, I have computed this scattering problem by assuming that I have an extra magnetic field. I was initially I was thinking that I would get a very non-trivial result. But unfortunately, if you put a magnetic field on such a surface, this surface is in fact has a finite area. It is non-compact, but it has finite area. So the magnetic field has to be quantized. And as a result, the phase shift, I mean, is not so different. I mean, the chaotic part of the phase shift is not affected by the magnetic field. The expression is different, of course, but the chaos, the magnetic field doesn't bring new chaotic effects. Okay. Okay.
Can I ask a quick question about this?
Yes.
If one looks at the plot of the phase, it looks totally erratic, like you said. How is there a way to quantify how chaotic this is?
I cannot really answer to your question, but you should look at the Gutzwiller paper. I mean, it draws this explicitly, and he mentions some theorems about the phase of the zeta function. But I mean, okay, they are general theorems, but to quantify precisely is not very simple, in fact, because you are very far from. I mean, no, I don't think anything is really known. This would be very interesting to have to find some precise link between this phase of the zeta function and the geodesics. In fact, this is a very interesting problem, but it is not easy, in fact.
Between what do you mean by between I guess we would say the Lyapunov exponent is just the curvature of the hyperbolic space, but that's not particularly exciting.
Sorry?
I guess if we were to ask about the Lyapunov exponent, we would just say it's the curvature of the hyperbolic space?
Yes. Lyapunov exponent is not interesting, but the geodesic motion on this manifold is very non-trivial, in fact.
Yes.
You have all sorts of geodesic lines. For instance, you have geodesics here, you have geodesics here. So it's very chaotic, and I mean, no one knows how to write them explicitly, in fact. And finding the precise link between delta of K and the geodesics is, to my knowledge, not known. But this would be very interesting. This is a very interesting problem. Another interesting problem would be also to understand what happens if you put a magnetic flux here.
That was exactly my
question. This
so
was done.
Of magnetic
sorry,
field.
Not a constant magnetic field, but a Bohm-Aronoff flux.
But that would simply mean that the total magnetic field is not quantized because the...
Yes, exactly. Yes. But this would bring probably some non-trivial effect in the phase shift. This has been partly discussed in the paper of Avron that I will mention at the end. There is also a nice paper of a Hungarian physicist, Levay, which has studied such scattering problems in the presence of several cusps. In fact, this is even more interesting. You can have two cusps. This means that you can think of a particle which enters here and goes here. Here, you have only one cusp at infinity, but you can have many cusps and you can have a very non-trivial scattering problem. But to my knowledge, no one has been really able to compute the effect of delta of K coming from Aronoff fluxes.
I have a question.
Yes.
Does it make sense to look at a plane at a constant y and see if you still see a quantization of the orbit, like Landau level or something like that?
In this case?
Yeah.
Okay.
I understand that you cannot decouple really the motion in the perpendicular and the...
okay, in this case, the Landau levels, this is an interesting problem. In fact, I don't know really. what I will show, in fact, what can be shown, because this is non-compact. And in the compact case, if you believe in the Selberg formula that I will show in a few transparencies, the Landau levels are not really affected. They still, they are the same. In fact, the cyclotron orbits do not see they do not see the fact that you have a compactification. Oh, but on this, in this case, I don't know. I don't know, to be frank. Okay, I don't know. And so let me briefly, maybe time is flying, so I don't know how much time I have.
5 to 10 minutes.
5 to 10 minutes. Okay, so very briefly. Okay, I will not. Okay, just this was a transparency to explain the Selberg trace formula, and but I think I have explained the main steps. In fact, all the steps are explained in what I said. So the Selberg trace formula. Okay, just let me comment it here. Is a formula for the partition, which expresses the partition function as a sum of terms over all periodic geodesics. Okay, but these periodic geodesics in practice, to find them, you have to compute, you have to find all the hyperbolic elements to compute their trace. And this is, I mean, this is a program that you cannot do analytically. You have to do that numerically. This has been done by some of my colleagues. And in this way, you can compute the spectrum. Okay. And now let me come back.
Question. Yeah. What about the zero modes?
Okay, in this case, no. In this case, the zero modes. No, when I said zero modes before, it was maybe it was a bit confusing. It was zero modes in the. It was not really true zero modes. In fact, these zero modes were zero modes in the x direction. Where is it? I mean, this wave function. I mean, it is zero mode in the sense that n here is zero. I mean, but this wave function has a non-zero energy, in fact.
But they are not periodic. That's my point, right?
Which one?
So these ones, they're.
Oh yes, they are not. I mean, they are. I mean, yes, if you change x in x plus something, this doesn't change, in fact. So this is a constant in x. So this is periodic, in fact.
But are they in the formula, or do you have to add them by hand?
I mean, here I have added them by hand, but yes, they are allowed. You can put them, and they should be interpreted as scattering states. Yes, you should put them, in fact. But in the Selberg formula, they do not arise, because the Selberg formula, in fact, is valid only for compact surfaces of finite curve with a finite surface, in fact, and which is not the case here. So the true Selberg in the true Selberg formula, you would not have such states. You don't have scattering states. So so let me briefly mention what happens when you put a magnetic field. So everything is more or less obvious once you have understood the classical problem. You have, so as you said, one of you said before, you have these cyclotron orbits, and they are quantized by this formula, but you have a finite number of such states. In contrast with ordinary Landau problem, you have a finite number of Landau levels, and then you have also these scattering states, which are very simple scattering states. So this is on H. Now, if you would like to compute this thing on gamma over H, this is much more complicated, because from the beginning, the problem is more complicated. In fact, the periodicity condition is not so simple, because in fact, what happens is that when you make an isometry, the gauge field is no more invariant, in fact. The gauge field changes by a gauge transformation. The magnetic field is invariant, but the gauge field is not invariant. So you get a phase. The wave function gets a phase when you make a translation, I mean, when you make an isometry, and this is this phase. And in fact, this problem, if you look in the maths literature,
Alain, can you increase the size a bit?
Yes, sorry. This problem, if you look in the maths literature, is discussed under the name Laplacian on automorphic forms. So in fact, the mathematicians didn't realize that, in fact. I mean, they studied this operator, but they didn't realize, no one of them realized that this was, the good interpretation is that this is the Laplacian with the magnetic field. But they did, all the maths were done properly, in fact, everything, which is quite remarkable, in fact. And, but now, as a physicist, our goal, I mean, our aim is to put some physics in that. And so this factor, this automorphic factor is just a magnetic phase. And there is a Selberg formula for automorphic forms that you can find in Esch-al book. And now you will have 3 terms. Here you recognize the usual Landau levels, which are not changed, in fact. You see, this is true for any compact manifold. This term,
So there is a rotation button on top of your screen next to the...
You have up here, you have a rotation.
On top, oh yes. Rotation. Oh, there's another one. Rotation.
To the full isometry here.
Yeah, exactly.
Gauche. This one gauche.
Rotation gauche. Okay, thank you very much. Thank you very much. So in this formula, you see that you have an extra term. I mean, the main term, which comes from periodic orbit, is this one. And you have a phase here, which can be interpreted as Aharonov-Bohm fluxes. And what is very strange, and this seems for a while mysterious, is the fact that this term is almost the same as in the free case. The magnetic field doesn't seem to change the periodic orbits. In fact, you have just the addition of this term. In fact, there is a very simple interpretation for that, and I will close with this. The interpretation is the following one. In fact, if you work in a proper frame, you can show that you have this periodic geodesic, which corresponds, when B equals 0. This corresponds to the periodic geodesic that I showed at the beginning of this talk. It corresponds to this hyperbolic element. But when you put a magnetic field, this periodic geodesic becomes this one or this one, depending on the initial condition. And when you compute the true action, including the effect of the magnetic field, you get what is written in the Selberg formula. In fact, everything is consistent with the physics. Maybe to understand more clearly what happens, I have drawn here the case of a sphere, which is more familiar to most of us. And if you look at magnetic geodesics on a sphere, this would correspond to putting a magnetic field at the center of the sphere. The Lagrangian is given here. So you have the free Lagrangian, I mean, free kinetic term, plus a term which comes from the magnetic monopole. And if you look at the trajectories, you can see that by writing the equation of motion, you can see that you have trajectories which are theta equal theta 0. That, I mean, you have such trajectories which are allowed, I mean, parallel lines. They are allowed provided this term vanishes, which fixes the velocity, the azimuthal velocity. So if the azimuthal velocity is fixed, this is an allowed trajectory. So in terms of the total energy of the system is related to the angle by this formula. So this means that for a given energy, you have two possible geodesic trajectories, which are given by tangent theta 0 equal plus or minus square root of 2e over b. So this would be the trajectory in the absence of magnetic field. When you put the magnetic field, this trajectory splits into these two trajectories here. This is exactly what happens in our case, and this explains the part of the physics of this Selberg formula. Okay, I will close with some references, and so I mean, Gutzwiller paper are really very interesting, and in my opinion, is the one who made the most interesting, progress in this field of chaotic dynamics in this context. And especially the link with negative curvature also he made. And there is a review paper of Balázs-Vorosz, which is very, very good, in old physics reports. And there are various papers which are quoted here. There is a paper of Avron, Klein, Pnueli on the torus, on the hyperbolic torus, and also some maths references which are here. I found this book very interesting, and the book of Bortwick, Introduction to Spectral Theory on Hyperbolic Surfaces. This is very nice and very readable for a physicist. And there are also recent papers of mathematicians which are inspiring. There is a paper of Zagier, Dynamics of Geodesics and Mass Gas Forms, which is very readable. And so I think there is plenty of work to be done from the physics point of view. Okay, thank you.
Thanks.
Thank you.